Okay, so we're back. You've got that chi-square value from the previous test. I'm going to walk you through a couple more examples before we talk about what that chi-square value actually means. So here's another example, trying to get you to understand just how useful these chi-square tests are. So salmon is a big deal in this part of the world, right? And we might want to restore salmon habitat. So to do that, we might need to understand what kind of habitat do salmon prefer. Right? So let's say we go out to a stream and we survey the stream, and it's composed of 55% sandy bottom and 25% gravelly bottom and 20% silty bottom. Okay. Then if salmon have no preference for any of these habitats, you would expect to find about 55% of the salmon in the sandy habitats and 25% of the salmon in the gravelly habitats and 20% in the silty habitats, right? They'd just be like randomly cruising around across all the different habitats, showing no preference. Does that make sense? Okay. So you can see how I've set you up with some expectations, right? And these are expectations given the null hypothesis. The null hypothesis that salmon have no preference for a particular habitat. Well, you might know something about salmon already, and you might have a guess as to what kind of habitat they might prefer, right? So what you do is you go out to a stream and you start surveying salmon spawning. And you record the type of environment that you find fish spawning in. And so you're just sitting there at the side of and you're like, oh, there's a salmon spawning. Oh, it's in the sandy habitat. Oh, that one's in the gravel, right? So you record the type of environment that you see salmon spawning in. And you might end up with a list like you see on the left. Now, again, keep in mind, these are categorical variables, right? Sand, gravel, silt, right? So a chi-square test would be most appropriate. So now you've got your data kind of tabulated. You sat there for a while. You saw 30 fish, 8 of them were in the sand, 18 were in the gravel, and 4 were in the silt. Now, how do you set up a chi-square test like this? Well, how many fish would you have expected in the sand? Well, from a total of 30 fish, if sand makes up 55% of the habitat, you might have expected to find 55% of the fish in the sandy habitat, right? So you would multiply the total number of fish by 55% to get the expected value if they show no habitat preference, right? So this is how we would calculate the expected values for sandy habitat, gravelly habitat, and silty habitat. You can see in the column, we've got observed values, and now we have expected values. So what do you think? Does it appear as though salmon prefer a particular habitat? You can compare the observed to expected values, right? It looks like they might observe the gravel habitat, but we'd need to run a chi-square test before we have confidence in our answer. And there's one thing back here. Take a look at the total. So the total is 30 fish. That's kind of an important number. And then there's 3 different groups here, right? 3 different categories. And so we need to understand something called degrees of freedom. The degrees of freedom are just the number of groups minus 1. So this data set has 2 degrees of freedom, and that comes into play in the table. And I will talk about degrees of freedom in another lecture. Okay, but just keep in mind that the degrees of freedom in this example are 3 minus 1 or 2. Okay, so if we use that same equation, chi-square equals the sum of the O minus E squared divided by the E's, then we would take each observed value and subtract its expected value, square it and divide by the expected. And you would end up with these numbers on the side. And if you added them all up, you would get 19.75. Well, this chi-square value is much bigger than the one from the milk example in the previous video, right? And so now we have to deal with, what do we do with these chi-square values? So how significant or how big does this chi-square value have to be to show us that the observed value is different from the expected value? That's the real crux of this test. And so we actually need a table of chi-square values to compare to. So here's a table of chi-square values. And what you can see is the degrees of freedom down the side, okay? And I told you in this example, we have 2 degrees of freedom. And then we have the probability that you would see a chi-square value that large due to chance alone. Now, it's very likely, so with a 99.5% probability, that we'd get a chi-square value of 0.01. Okay, moving across the table, our value was like 19, right? Well, moving across the table, we can see that we never get 19. So the probability of getting a chi-square value of 19 is very, very small. And that means that basically the observed values are not equal to the expected values, and the salmon are showing a preference. Now, I've highlighted in red what's called the critical chi-square value, and that's at the probability of 0.05. And this is a really important value. It's called the p-value. If your p-value is less than 0.05, you can reject the null hypothesis. So as long as our chi-square value is bigger than 5.991, we can reject the null hypothesis and say, actually, salmon are showing that we would reject the null hypothesis that says salmon show no habitat preference, and we would say, yes, they do. They actually prefer the gravel habitat based on our data. Now, remember back to the milk example, and our chi-square value was 0.099. Well, that's much less than 5.99. And so in that milk example, we could not reject our null hypothesis. And we would have to say, even though there was quite a lot of variation in milk fat in that 2% milk, it was not different than 2%. And so it deserves to be on our grocery store shelves. I hope that makes sense. Okay, this is a really kind of complicated point, and we'll come back to it in a couple other lectures. Okay, so just so you can see, this is kind of maybe ahead of the game here, but this is what the distribution of chi-square values looks like, and you can see the probability on the y-axis and the chi-square value on the x-axis. And you can see how that probability function changes through time. We're going to come back to these distribution functions. So if that's confusing, just hold on to it. We don't need to worry about it. Okay, so back to the salmon example. We could interpret our results in this way. Salmon show a significant preference for specific habitat types. And we would say chi-square with 2 degrees of freedom equals 19.75. P is less than 0.05. And in fact, on this table I highlighted here, our value is even bigger than 10.597. So that's why this says P is even less than 0.005. So we reject the null hypothesis, and we would say, in fact, salmon appear to prefer gravel habitats. Notice in this interpretation of the statistics that all the stats are kind of contained in parentheses. I'm not writing about p-values and chi-square values and null hypotheses. I'm writing about salmon and their habitat preferences, right? And I'm using the statistics as evidence to support my claims. And that's really important in terms of interpreting results. Okay, so now we're going to learn about Mendelian genetics a little bit and how we can use a chi-square test. So you may have learned that there are different types of peas, and in this case, you might have yellow peas that produce some green and yellow progeny, and then if you cross them, with a green pea, you might get a different proportion of green and yellow progeny. And so we can use an example from Mendelian genetics. If you were Mendel and you were growing lots and lots of peas, you might have ended up with some of these observed values. So for a big study, you ended up with 315 round yellow seeds, 108 round green seeds, 101 wrinkled yellow seeds, 32 wrinkled green seeds out of 556 total seeds. Now, Mendel's expectations are that you would have found these different types of seeds at an expected ratio of 9:3 to 3:1. Now, you could figure out your expected values by taking 9/16 of the total number of seeds in your study, 556, to give you 312 expected round yellow seeds, 3/16 to get you 104 round green seeds, 3/16 to get you 104 wrinkled yellow seeds, and 1/16 to give you only 34.75 wrinkled green seeds. Now in this case, the degrees of freedom equal the number of, it would be the same thing. Basically, you have 4 different types of pea seeds, and so 4 minus 1 equals 3. In this case, there's also 2 different columns, but 2 minus 1 equals 1, so it's the same thing. You can calculate degrees of freedom in a couple of different ways, but focus on just the 4 different types of seeds. Minus 1 would give you 3 degrees of freedom. Okay, so if we were to do the math, and you can see the math over there, you could do it on your own. 315 minus 312.75 squared divided by 312.75, right? So it's the same equation using every observed minus expected value squared divided by the expected value and summing them all up. We would end up with a chi-square value of 0.47. Now, we would have to go to a table using 3 degrees of freedom this time. And we would find that using 3 degrees of freedom, we would need a critical chi-square value of 7.8 to reject the null hypothesis. And in this case, the null hypothesis is that the peas that we observed meet Mendel's expectations, right, of 9 to 3 to 3 to 1. And since our value is 0.47, we come nowhere close to that. And so we would not reject the null hypothesis, and we would conclude that these values are actually in the same ratio that we would expect. Okay, so they live up to the expectations of Mendel's laws of heredity. The null hypothesis is accepted, and the data fit this 9 to 3 to 3 to 1 ratio. Okay, so I hope that makes sense. I'm going to walk through some of these examples on the chalkboard if you weren't able to follow some of the math. And so you should have some other examples to work through as well. Good luck on the stats lab and the Quizlet. Don't forget to take the little Quizlet.